This meeting is being recorded.
Good morning, everyone, and welcome back to our AI seminar series. On the screen, you can see the seminar for the next week. Please try to attend next week as well. Today, we have Razvan Pascanu from DeepMind as our speaker. Razvan did his PhD with Professor Bengio, one of the godfathers of deep learning in University of Montreal, and he has made a variety of impactful contributions to deep learning, including in optimization, recurrent models, graph neural networks, and continual learning. He's also very active in promoting AI education and is the main organizer of the conference on lifelong learning agents, which was held recently, and the Eastern European Machine Learning Summer School, and other workshops in Europe's ICML and iClear. And today he is going to give us a talk with the title Challenges in Deep Learning. With that being said, I leave the stage to Razvan.
Thank you so much. Thank you for having me, and thank you for the introduction. Okay, let's see how this works. Okay, so the same, I already had the title slide, so I kept it in. But basically, yeah, today I'm gonna try to go through a few challenges or open questions in deep learning that I think are extremely interesting. And on this slide, mainly, I just wanted to highlight my email address. Like, if you have questions and we don't get to go through them in the presentation, feel free to ping me by email, and you know, we can keep the discussion going. And just sort of as an outlook of what I'm trying to do here, I think one of my goal is just trying to introduce a little bit my myself and my research, and yeah, the kind of research directions that I think are interesting, and I'm trying to motivate you to look at them. And because of that, hopefully it's going to be a coherent story. It might feel a little bit patchy at times because maybe I'm going to kind of jump between topics. But I want to focus on two main themes. So one of them is it's about adaptability, or the ability of a system to learn on the fly. And the second a big theme that I want to talk about, it's the role of inductive biases, because I feel, I mean, depending on who you talk to, at least a couple of years back, if you talk to typical deep learning researchers, a lot of them were very focused on letting the data speak, and weren't that keen to talk about inductive biases. And yeah, if you have questions, feel free to ask them. So I guess using the Q&A seems to be the suggestion, and yeah, I'm happy to take questions throughout the talk and at the end. And finally, most of what I'm gonna talk about, it's sort of the outcome of research that happened with a lot of amazing colleagues and collaborators. And I'm gonna try to point to papers and names, but yeah, just trying to highlight that there is a lot of people behind all of this work, and my part was actually quite small. Okay, so let's talk a little bit about the importance of adaptability. So the way I see sort of our field in general is that it relies very heavily on performance. And you know, typically, if you look at papers, you see plots like this ones, where you look at performance, particularly you look at performance, you know, compared between other systems over years and so forth. And there are good reasons why everything is driven by performance, right? Why the performance is the main thing that we seem to be measuring in our research. And that's because it makes it very easy to have benchmarks and to have leaderboards, right? There is one number that you need to beat, and that makes research clean. And it has also you know, practical implications. Like when you're trying to build a product out of some machine learning tools, you do care about the performance. You do care about how the system is going to perform in practice. But it is a simplistic view of what we really care from these systems. And particularly like now, since I mentioned sort of the idea of product and trying to use machine learning in the wild, when you try to do that, you realize that there is a lot more that you want from a system besides performance. And I've tried to here summarize like four different things that I think are extremely important. There's obviously a lot more, and yeah, but one thing is whenever you have a system that has to interact with the world is changing, right? And the system somehow needs to deal with this, and the world can change in unpredictable ways. So that puts a lot of pressure on sort of the typical way of how we deal with these systems, where we assume everything is stationary. The second issue with this focus on performance is it very easily you end up trying to think about like one size fits all kind of solutions, right? Where and then you see this everywhere. There's this big focus on this very large foundational models or large scale unsupervised models, however you want to call them. And they, the goal is to build one system that can do everything. And of course, one size fits all kind of solutions can easily be suboptimal. Ideally, you do want solutions that can specialize for exactly what they need to do. The second bit, and this is maybe a bit less clear or harder to describe very clearly, but this idea of performance as a metric, it's only well defined in sanitized scenario. So it's very hard to talk about how you want to evaluate, like the train test protocol that we rely on. It becomes a bit unruly when you scale things too much, and when you're working with real data. So it's like dealing with train test contamination and all of this kind of stuff becomes extremely problematic and hard to define. Um, and the last thing is, when you're just focusing on performance, you end up getting stuck in this loop where you just keep scaling things up and keep collecting more data. And this creates all kinds of bottlenecks. Data is not the only bottleneck. Actually, computation becomes a much bigger bottleneck, and this kind of prevents doing a lot of things like like proper checking sort of your system and the hyperparameters of your system and so forth. Um, and I guess the hypothesis that I'm trying to focus here, the way I'm trying to think about this, so I, looking at all of these problems, the way I'm thinking about it is that there could be one way to move from performance, and that's to think about adaptability, to think of systems that can continuously learn, the systems that learn on the fly, um, and think of that as a sort of the main the main mode of operation of your system, and then trying to think of like, if you have a system that continuously learns, then what does it mean for this system to perform well? And just to go back over the reasoning and try to kind of cement this idea a bit further. So I guess the hypothesis here is that we can't have a static system that learns and that's it. And the reason because of that is that um, when you're trying to do this, one thing that you need to do is you need to cover everything that you care about. So if you want to learn a system to predict cars, then it needs to cover the distribution of all possible images and be able to distinguish a car versus non-car in all of those images. And um, I would argue, again, this is potentially almost like a philosophical question. There are people out there that believe that such a system can exist, like a static system that would be able to do this kind of things. But I would argue that it's a really hard thing to achieve. Even if in theory one could build such a system, you have all kinds of issues. Like when you're talking about coverage, so say you want to cover the distribution of natural images, like how do you measure that? How do you even define that? Um, when you're talking about languages, you have this kind of issues where you have sentences. There's just one word difference between two sentences. Are those sentences similar? Are they very different? When does one like particularly when you're thinking about test train contamination, when is there a contamination when the only difference might be like a letter or like a word in the sentence? Um, how do you collect data if the goal is to have this system that would be static? How do we know that we've collected the right data? Like, how do we ensure that this data collection process is going in the right way? And how do you evaluate the system? So like this problem of contamination is quite hard. And um, the idea of having a test set that somehow is representative of this distribution, it's also something that's somewhat hard to achieve. Another big problem is, and I don't know, like to a certain extent, this used to be I mean, I think it's still a big theme. It's all this discussion about out of distribution generalization, or systems that are able to generalize very well. And again, this is something that's I think is very intriguing. It's definitely something that we want. We want systems that can be able to extrapolate, but this again is something that's really hard to define. What does it mean to have OOD generalization? OOD generalization with respect to what? Like no free lunch tells us that we're not going to be able to have a system that will generalize to any arbitrary thing. Um, and we're back to this kind of similar issue of like defining coverage and defining I guess distributional shift, defining the relationship between data. So how can having a system that continuously learn can fix this? So I don't think fundamentally it fixes this. It's not going to answer all of these questions. So I don't think that there is some kind of magic bullet where if we change sort of our metrics, somehow we don't need to deal with all of these problems. But what adaptability can do is it can change our perspective. In particular, now we have to think about how quickly can a system track a change in a distribution. And my thinking is that if we switch into measuring this kind of metrics for our systems, then we might be better able to deal with all of these problems. Like some of these problems become slightly more tractable. And it might be easier to move forward. And I wanted to also like highlight another thing that kind of led me to focus on continual learning and focusing on adaptability. And this is part of this hypothesis that Thomas Griffiths put forward in one of his papers, um, where he argues that the profile of human intelligence is due to its limitation. And like I mean, yeah, maybe I'm misinterpreting what he's trying to say in that paper, but one example that he gives and that kind of motivates sort of my understanding of his hypothesis is this example of AlphaGo. So AlphaGo, this bot that is playing the game of Go, at some point was playing with World Master, and it does this move that no one could understand, and that it was crucial for the system to win. And Thomas Griffiths' argument was that the reason why this move seems so unnatural to us is because we as humans, when we're trying to play this game, the way we do it is by decomposing it into sub goals. And that move had no meaning in solving any of the sub goals, right? And the only reason that AlphaGo can see that move as a winning move and a move that it needs to do is because it does not try to decompose the problem at all. So AlphaGo, it's kind of like a brute force system that only cares about winning the game. It doesn't have any kind of, maybe, you could argue that it does something smart internally, but in general, like it looks at the entire problem. And the argument goes that why do we as humans try to decompose the problem into sub-problems and solving that way? And the reason is because if we do it that way, it is more efficient. And we have to do it that way because we have limited computation. So compared to the AlphaGo system, humans have, because we're biological system, our amount of computation that we can do is considerably more limited. So basically our limitation defines the kind of solutions that we have. And I think this is something that we should embrace in machine learning a bit more. So I think in machine learning, we usually think of these things as limitations that we have to deal with, and we struggle with, and we're trying to, but like really all of these limitations like computation, computationally and so forth, they can basically shape our loss surface. So they can shape what kind of solutions we like. So potentially one way to get, say, a system that does compositionality is by restricting the amount of computation that system can do and then trying to solve the problem. And then potentially the only possible solution that the system can find is one that relies on compositionality, because there's no other way of solving this problem very efficiently. So yeah, the other hypothesis that I think goes hand in hand with the speed of learning or learning on the fly is this idea that we should actually exploit limitations and use limitations on our systems as a way of shaping the loss surface and shaping sort of what the system can do. And yeah, I guess sort of in one stroke, like what I guess I'm arguing for is that we kind of somehow need to move on from performance to another kind of metric that is not just looking at performance, but it also takes into account the cost of learning, the cost of inference, maybe the amount of information that's been hard coded in the system and so forth. Of course, like you can try to write a formula. The formula I wrote probably makes no sense, but obviously this is not something that we can really compute, right? So the formula that I wrote down, like we don't know how to estimate any of these quantities. And also, like when we're thinking about cost of learning, I think typically, at least in machine learning, there's quite a big community that's focusing a lot on data efficiency, and I think it's also important to think about computational efficiency and stuff like that. So yeah, I mean, I guess sort of at a high level, what I'm trying to argue is that I think for the community, it's sort of a really good time now to shift from focusing just on performance to focusing on something like agility or ability to learn, and focusing on how efficiently we are extracting information from data. And if we focus on this, that will kind of shift how some of these problems that we're facing, how they look, and it might provide a different way of approaching them. I think something similar had happened, for example, when people got super excited about meta learning, and even though you'd have the same problems that you'd had for the learning system at the meta level, just having that shift and thinking of the meta learning system rather than thinking of the system that learns helped to kind of push certain things forward. And my hope is similarly, if we start focusing more and more in our research on the speed of convergence and so forth, it will somehow change the problem enough that we might be able to make some interesting progress and coming up with systems that do way better. Um, and then maybe the one thing that I wanted to highlight at the bottom of the slide is that while this might change a little bit our perspective, it does not fundamentally solve all the problems. In particular, like one big problem when you're talking about non-stationarity is the distributional drift, right? It's talking about the relationship between the data that you observe. And just because now we're looking at how quickly the system can incorporate new information, it doesn't mean that we can avoid talking about relationship between data. Because of course, this speed of learning would be conditioned in how the data is changing, right? Again, we're probably facing like a no free lunch. So it's not going to be that our system is going to be optimal at incorporating information for whatever information you're giving to the system. It has to depends on the relationship between the new information that it gets and sort of whatever it learned so far. And this is in my mind is still like one of the big problems in the field. And I mean there are lots of people that know a lot more than me about this, but I think we need to kind of keep building on the tools that allows us to formalize and describe this relationship between data distribution and between data points. And we have some tools. So I know a lot of people were excited about talking about symmetries and invariances and sort of the geometric view of deep learning. So there's definitely a tool that we need to see how far we can push and try to understand. I do find it that it's a little bit rigid at times. So I find sort of symmetries and invariances and this kind of things not being flexible enough to describe the kind of relationships I might care about. But this might be just sort of like a momentary thing, and it's just sort of a question of understanding these tools better and pushing them forward. Causal structure and causality is becoming a huge topic, and part of it is because you can use causality to reason about sort of how the distribution is changing, how the talk about distributional drift, you're talking about sort of changes in the causal graph and trying to understand what is constant and what has changed. And again, this is a great tool, and it's I mean, it's gaining quite a bit of popularity, and I know a lot of people at Mila and Yoshua Benjo for sure. It's a big is putting a big bet on causality being sort of one of the main tools that you can use to think about sort of non-stationarity and to think about how the system should adapt and how the system should reason about out of distribution data. We should not forget probabilistic tools like divergences and metrics and so forth. I don't think at the moment the way the things I know of, I don't think they're that useful as tools to describe relationships between data, but it is a very powerful framework. So probably there is definitely something in there. Another thing that's maybe a bit more niche, but I got kind of recently got excited about is all of this discussion about algorithmic alignment. So this is quite popular in graph neural network literature. And in particular, I think there is a quite fast-growing community of people trying to use category theory to describe computational graphs that are being the computations that are being done by neural networks. But you could use these tools in the same way to talk about the computations that are needed for the generating process. So if you have a generating process that generates the data, you can you can use similar kind of tool, and now you can see if you have two different generating processes, how aligned they are from from a bird eye view, using category theory and this kind of tools. And I guess one paper that got me excited about this is the recent work from Petar and Andrew Dudzik, who are colleagues at DeepMind. But of course, like, we have these tools that probably this list is definitely not enough. There's probably a lot more other things out there that I'm not aware of. But do we have do we have the tools? Are these tools one and the same? And that's a question that I find quite interesting. And I'm pretty sure that there is some equivalence, at least in the way we might be using these tools. Yeah, I think this is a very interesting, a very exciting sort of research direction that we should push forward. Okay, cool. So I've been okay. So there is a question. Isn't the efficiency of extracting information or explainability directly or indirectly equal to the performance of the model? How can we change our focus to the former when both are related? I don't think they are the same. So basically, I think that the kind of stuff I'm thinking about is more similar to sequential learning, where what you're trying to look is at the area under the curve, say, well, it's not really the training error, but you can look at the area under the curve for the training error, and you're trying to reason whether a system is learning more if, it takes fewer updates and needs to see less data in order to get similar performance. So I think the issue with performance is that we don't care about how much compute the system had to go through in order to get that number. While when you're thinking about efficiency, you're asking yourself, if I get a few more data points, how quickly am I going to incorporate that information? And I think it's slightly different. I mean, I see your point that in the end we're working with performance as well, but what we're working with really, it's, I guess, sort of like an integral of performance over some quantity, and I think that is sufficient to change things. Yeah, I don't know if that answered your question. I hope it did a bit, but yeah, I don't believe they're the same. They are related, and to be honest, I think that's one thing, right? Like, we can't jump too far from what we have, or at least I don't. It's really hard to jump really far from what we have. So obviously, if we want to move away from performance, we're going to move to something that is very related to performance, but change in a little bit, because like we don't like to say that we don't want to do incremental things, but science is incremental in nature. Like, we can't, it's really hard not to just kind of build on what you have. But sometimes you just switch perspective a little bit, and it's sufficient to open doors that were closed before. And that's what I'm kind of thinking about. But yeah, I hopefully, as I go forward, maybe I'll have some examples that makes it a bit more clear that they're not really exactly the same goal. So continual learning, yeah. So as I said, like, in the last few years, I've been focusing a lot on continual learning, and part of it is because I feel like continual learning is the sub community that is trying to address this problem of how do you get the systems that are learning efficiently, that are incorporating data efficiently. Obviously, so if we go, so this would be like a definition of continual learning. You can find many definitions of continual learning. You can, these definitions tend to be very mechanical, right? So they talk about, like, oh, like, what do you have to do to be in a continual learning setting? And it's usually you have a sequence of tasks and you have to learn them one after the other. And then there's some requirements for you to be doing continual learning, right? Like, what is the solution of the continual learning problem? And this is an algorithm that is able to go through these tasks and do not forget, and speed up, have forward transfer. So, like, accumulate knowledge from one task to another, so that when you learn a new task, you can use that knowledge, and so forth. And then that's why, sort of, like, mechanically it feels like slightly different, but I think in principle the core idea behind continual learning, or what people would really wanted when they started thinking about continual learning, is this idea that you want a system that learns in a world that is non-stationary, where data distribution changes. The concept of task and the partition of the continual learning problem into task is just sort of a tool that we use in order to be able to generate metrics. It is not fundamental in any way to the continual learning problem, and ideally I don't think anyone who's working on continual learning, they would prefer not to have the concept of task, because as we know, task in itself, it's a very ill-defined term. Like you always have a, it's always hard to say what is a task and what's not a task. So in that sense, task is just a construct that is kind of useful and it's a bit arbitrary, but it's not fundamental to the definition. What's important to the definition is that we're not assuming IID, right? It's not an IID distribution. It's a non-stationary distribution that can change in all kinds of ways. And you want the system to learn in this kind of setting. And what you want is that the system accumulates knowledge and somehow makes use of that knowledge. And forgetting is sort of like a byproduct of that. So the reason why we've been focusing so much on forgetting is because when you're thinking of a system that accumulates knowledge and uses that knowledge to learn faster, well, the first question is, does it accumulate knowledge? And how do I test it accumulates knowledge? And the easiest way is test to see whether it can still do the things it used to do, right? If it accumulates knowledge, then it should not forget. And I think, but of course, like we can argue a lot. I feel like the definition of forgetting and accumulation knowledge, they're not one-to-one, right? So a system can forget to execute previous tasks while still keeping track of a lot of knowledge that it has accumulated in the previous tasks. But anyway, like usually continual learning is given as a list of desiderata that we want from these systems. It's a field that it's very related to online learning. And actually, I feel like people don't acknowledge this enough. There is a lot of commonality between the goals of online learning and the goals of continual learning. But what is potentially specific to continual learning is that it focuses a lot more on deep architectures and sort of all the messiness that comes with that, having that nonlinear function approximator in there that kind of makes it hard to do any kind of theory and kind of forces you to do all kinds of other things that you'd probably not need to worry in sort of typical online learning settings. And the issue that we have with continual learning right now as a community is that this list of desiderata is not sufficient to ground the goals of continual learning. First of all, they are in contradiction to each other to a certain extent. So, things like having perfect recall and fixed capacity, we know we can't have both, right? So particularly if you have an infinite sequence of tasks. So something has to give. And the question is, what is that? Forward and backward transfer, again, with forgetting, they seem to be usually fighting each other. And we're going to have examples further on where it seems that you're trading one for the other very explicitly. You have this, you have this requirement of like, oh, you need to maximize forward transfer, but then how do you even quantify that? Like, what are you supposed to transfer, right? And that kind of goes back to what is exactly the non-stationarity we're dealing with, and what am I supposed to exploit in this non-stationarity, right? Because there could be no structure in how the distribution is changing, and then there's nothing to exploit, there's nothing to transfer. So the question is, what kind of structures are we meant to focus on, and what kind of structures are useful? And this is something that the continual learning problem does not give you. It gives you, it provides it implicitly through the benchmark that you might be using. So you fix the benchmark, and now you fix the type of distributional drift, and now you're kind of, but it's not necessarily a distributional drift that we care about. It's not something that we thought about. They just sort of whoever created that benchmark, whatever they decided to put together as a set of tasks, that's sort of the distributional drift you have to deal with. And because of this, like, I think what's important to realize is that continual learning, it's a collection of different kinds of problems. And it's not that one problem is not meaningful and the other one is more meaningful or anything like that. Like, all of these problems are meaningful, and all of these problems require different kinds of trade-offs. So there's not like one solution fits all for continual learning. I don't think so. I mean, I'm pretty sure at this moment in time that that we're going to have lots of different kind of continual learning solutions that are specific to different kinds of scenarios and different kinds of distributional drifts, and different kinds of wants that we might have depending on what we want to exactly do with that system. So if that's sort of what continual learning is, then how do we navigate this space, right? How do we deal with this? And I guess what I wanted to say in the next few slides was that one way to deal with this is we can ground ourselves in different ways of understanding why we're doing continual learning. And so like the first example that I have here, so this was proposed at the workshop in 2021. It's what they call what they've coined as being continual semi-supervised learning. And the idea here is to basically just look at applications. Are there applications that have us, and just do exactly what the application required. And the setup that they have here is something where you have a large scale supervised system that you've learned, and now you want to adapt the system because the world is changing. So say this is an image classification, but now you've collected more data because you've interacted with your users, and now you want to adapt the systems to the new data. But you don't want to label it because that's kind of expensive. So the next kind of tasks are unlabeled. And then, they've proposed like a few benchmark in this space that are very kind of grounded into like real case scenarios, right? And a lot of it is based on vision, but it can be also based on language. And they're kind of emphasizing quite a bit sort of this interplay of not labeling to save money, right? So the idea would be you have some initial maybe label data, and then you have a lot of unlabeled data that is continuously coming at you, and you want to update your classifier in such a way that the things still work. Another way to ground sort of the continual learning problem, and it's reinforcement learning. And sometimes people, I mean, you'd have people, and I think Rich Sutton at some point said this, that continual learning only makes sense in reinforcement learning. Of course, you'll have people that say continual learning makes sense outside of reinforcement learning, but definitely there is quite a there is a difference, right? There's the reinforcement learning variant of continual learning, and then there's a non-reinforcement learning. And the reason for that is because reinforcement learning is a very natural place for this kind of continual learning, because even if you don't do anything, as soon as you start doing RL, the observations that you see, the distribution that you see, depend on the actions that you have. So there is some form of non-stationarity. And if you add the function approximator, so you do deep RL, then things get very messy, because the function approximator doesn't like non-stationarity, or at least we believe it doesn't. Like all the optimization that all the proofs of optimization, everything that we know about deep networks is that it prefers things to be IID. If you make things IID, everything works better. So you have these tensions between the two. And most of the time we tend to solve this in very brute force way. So like when DQN came out, so one of the first mix of neural networks and RL, the solution was a replay buffer. And the replay buffer is there to do different things, but one thing that it does, it provides a somewhat stationary distribution to the neural network that it was training, and that was kind of crucial to get that neural network to learn efficiently. When you move to multi-agent systems, this problem becomes even more acute. Like you have the non-stationary is even bigger, and then again, like people tend to solve this with like kind of brute force kind of solutions. So for example, in StarCraft we had what we called a league of experts. In AlphaGo as well, you do self play, but you'd have to keep track of a bunch of previous versions of yourself. And the reason for that was because if you just play with the best version, the previous best version of yourself, you end up in this cycle where you forget how to deal with specific policies that were in the past, and you kind of end up in a cycle. So the only way to deal with that is you need to keep copies of different agents from the past, and try to IID fashion play randomly to some of this. And it's not as simple as that. So like if anyone is really interested in this and looks into a StarCraft paper, there's like all kinds of logic in how you select from that league who you're playing against, and there's some formalism there, some math and some game theory ideas there of how to do this optimally. But in the end, part of the problem is exactly this, is that the policy that you're learning is forgetting how to deal with some of the previous policies. And the only way to deal with this is to force you to play against all the possible previous policies that you've seen. And this is a CL problem, right? And there could be more elegant solutions besides the brute force approach. I also talked a lot about efficiency of learning. I just, because I wanted to highlight a few papers as well as I go through. I wanted to highlight two papers that I did with colleagues in Poland. So this is in one paper we tried to introduce continual world, and in the other one we're trying to understand what is, we started with the hypothesis that continual learning is continual learning. It doesn't matter whether it's RL or not, and we're trying to understand, what are some of the RL specific aspects of continual learning? And yeah, I guess maybe just to in 2 words to kind of highlight some of the findings of this paper. So I guess the first paper, what I really liked about it is one of the it's among the first papers that are trying to push a bit more this idea of looking at forward transfer. And in particular, one thing that we do here is we're trying to define what would be conceptually an upper bound. And to do that, we use the transfer matrix. So what we do is we say, like, look, if you'd have a continual learning system that is working somewhat, then if I'm looking at forward transfer, I should see this at least the same amount of transfer as if I'm just fine-tuning from the previous best task. So, if I have K tasks before, some of them act as distractors, some of them act as being quite similar. If I just pick the one that's most similar and I just fine tune from that, that's kind of my target. That's sort of what I would expect my continual learning system to be able to do. And what we show in this paper is that, well, the systems do not do this. And in particular, what we also see in this paper is that it seems there's quite a direct trade-off between forward transfer and catastrophic forgetting. So any system that is trying to deal with catastrophic forgetting learns slower. And yeah, so it seems that most of the algorithms that we're doing, because in the past we've been focusing so much on catastrophic forgetting and making sure the system doesn't forget, and neglecting to look at forward transfer, all of this algorithm seems to be trading off forward transfer in order to fix catastrophic forgetting. And for the second paper, when we were trying to look at transfer in continual reinforcement learning, we found like quite a few interesting things, and maybe they're not that surprising for RL people, but like one thing that we found that for me it was kind of surprising, and maybe this is the only thing I'll mention about the paper, is that actually transferring features in your neural network is not that useful. It seems that the most gain you have is if you just use the previous policy to collect data, and fill up your replay buffer with that. So it seems that the quality of the data, at least in the task we considered in there, completely overwhelmed any kind of feature transfer or any kind of initialization that you could get to your neural network. So that to me was a bit surprising, because if you think about continual learning and supervised learning, it's mostly about feature transfer and sort of trying to understand your previous representations. Okay, checking the time. Another thing, again, like as I mentioned before, is sort of the speed of learning. I think this is a very interesting perspective, and I guess sort of just to kind of go a bit deeper into it and talk a little bit about the implications. So if you're thinking about the speed of adaptability as your target, then learning becomes this kind of tracking problem. So what you have is you have a target that keeps changing because the distribution under the hood changes, and what you're trying to do is you're trying to track this. And I think this is, I think this is kind of exciting perspective, because if you're thinking about most of the work that happen in optimization, it's usually about convergence, right? Like the way you think about optimization is you have the static loss surface, and you're trying to converge to a minimum, to a fixed point. But now there is no fixed point, and because of that, like many of the choices that we do in the optimizers that we use, like Adam and so forth, might actually be wrong, because they might, maybe they're a bit too aggressive, and that's actually a problem. And connected to this, I mean, there were like recent papers, I'm pretty sure many of you might have heard of them. So there's the original work from Jordan Ash and Ryan Adams, when we try to do a bit of research in that direction as well. Rhys Sutton and colleagues also worked on this. Is this idea of loss of plasticity. So one thing that seems to happen to neural networks is as they learn, they lose plasticity. So and this can, there are two different phenomena here that is useful to split apart. So one of it is the one that Jordan Ash and Ryan Adams focused on, which is saying that if you learn a task A, in their case, their task was half of CFAR. Then when you learn the task B, which is full CFAR, you cannot generalize as well. So you don't have any optimization issue. You can get your training error to go to 0 or whatever. But when you're looking at the generalization, there is a generalization gap that you cannot cover. And we know this to a certain extent. So there's for example, I have on the slide the paper from Google Fox and so forth on the extreme memorization, where we basically know the initialization controls how well you generalize. And we know that there are tricks that you can do. So there's ways you can initialize your neural network such that your neural network can, have 0 training error, but be chance on the test set. And basically, what I guess Jordan Nash and Ryan Adams' paper show is that, well, if you have a system that continuously trains, so if you think of this as a sequence of fine tuning, the outcome of fine tuning on task A might not be a great initialization when you fine tune on task B, because it might lead to this kind of generalization gaps. And to what extent this is a big problem or not, I think we don't know, but it's definitely kind of interesting to think about. And the second aspect of this kind of loss of plasticity, and I think to a certain extent the work from Rich Sutton's group is focusing more on that, is this idea that actually optimization might break down. So the problem that's happening there is, if you keep learning, at some point, for whatever reason, just optimization breaks down and you cannot minimize the training error anymore. And this can happen for various reasons. So one observation is, it seems that the weights of the network keeps growing over time, and that implicitly means that the curvature becomes less and less well behaved. So that makes optimization hard. Another thing, and I think that's used, one of the ideas that the paper is trying to latch on, is this idea of effective rank. So there have been plenty of observations before where it seems like as you learn, the neural network is losing effective rank. And what that means is, people, what they tend to do is they look at the covariance of the features of the penultimate layer. So just compute this covariance matrix, and they look at the rank of this matrix. And this rank decreases over time, which means that you're using less and less units to represent sort of the data. And their argument is, well, if learning leads to us losing rank, then at some point when new data comes in, we have a bottleneck in our architecture and we can't learn anymore, right? We don't have the capacity. We're basically losing capacity as we learn, so we don't have capacity to incorporate more information. I wanted to, just to continue the random papers presentation, I wanted to say that, like, it's a very difficult, and one has to be very careful with this thing. So there's some work that we've done with colleagues at DeepMind, with Chalar and others, and like what we're trying to show here is that actually losing capacity can be extremely important. So capacity is sort of how the model deals with robustness. And if we have a system, if you force the system not to lose capacity, depending on the task, depending on the data, depending on many other things, you basically again can break learning. So it's basically, I guess, it's not that it's as simple as saying lose capacity is bad, full capacity is good. There are some trade-offs there, and it is natural for the capacity, for the system to kind of construct this kind of bottlenecks while learning. The question is how to properly control this, right? How do you make this not to be catastrophic? And the other thing that I wanted to highlight, we're looking at this reinitialization. So one typical solution to all this kind of loss of capacity, it relies on reinitialization. And you have things like shrink and perturb. This is the original solution proposed by Ryan Adams and colleagues, but there's many other kind of reinitialization schemes. And we're trying to see, do this reinitialization really work? And again, it's a little bit problematic, because it seems like they do work in sort of kind of restricted scenarios, but when you're trying to say apply them to a very well-tuned pipeline, they seem to break down. So again, kind of confirming maybe a little bit what the other thing was saying, is like, well, it's not that trivial to decide what you have to do. It doesn't seem like always that the right answer is you somehow have to maintain capacity of your system in order for the system to train. And yeah, I'm not really providing too much details of what really happened in the papers, but yeah, if you're interested, I'm happy to discuss. So how much time do we have left? Okay, I'm just gonna go. Okay, I'm just gonna go over a few more things and then kind of stop there and sort of get questions. So I think I'm not gonna talk that much about inductive biases, because I think I took a long time to talk about continual learning adaptability, but that's great. The other thing, and this is something I've been thinking about for a little bit, is this idea of credit assignment in neural networks. So another way to think about all of these issues that are happening with neural networks and continual learning is just to think about gradient descent, because in the end, when we're thinking about neural networks, we're implicitly thinking about gradient descent. That's sort of the main tool that we have to optimize the systems, and that's sort of what we do day to day. And if you think about what gradient descent does when you're computing the gradients, well, you're basically independently for each weight, for each example, you're trying to ask the question, okay, if I increase this weight a little bit, would my loss decrease or would my loss increase, right? So you're making this kind of independent decisions for each weight, each kind of data point. And then when you're averaging over a mini batch, it's almost like each data point is voting, right? Some data points would say, oh, I want to increase this weight. Some data points would say, oh, I want to decrease the weight. And when you average them, you get the outcome. And you can think a little bit of this like a tug of war game. And I really like sort of this image. So you can think that what happens in learning, well, you have different parts of your data and they're trying to pull on each weight independently. And, they're trying to pull it one way or the other. And the way learning happens is you find an equilibrium, right? Everyone is pulling on the rope. At some point, forces are equal and you stop moving. And that's when you converge. And what is the implication of this kind of learning dynamics that gradient descent rely on? Well, one thing is that's why we need to have IID data, right? Because the only way learning happens is if you have all your data points pulling on the rope. When you cannot have that, you can sample it. So, but then you need to have in expectation, you do need to have all data points equally there for that kind of tension to still exist. So that's sort of where the IID assumption comes from. Another direct outcome of this is that there's no explicit knowledge composition, right? So you're not building on the knowledge. You don't learn data point B in relation to data point A. You're not building as like, okay, this is what data A is and data B is by just adding this little bit on top of that. You're learning them by constantly contrasting them, right? And yeah, I mean, and I wanted to give this as an image, and this could be like a motivate. This, like the way I think of this is just another way to motivate and to think of like what is the goal of continual learning. So as I said, in general, if you're just taking the usual list of desiderata that people give you when they define continual learning, it becomes very ambiguous what really is that we're trying to do. But when you have something like this in your mind, then yes, continual learning is about how can we improve credit assignment in the neural network? How can we learn in a way that actually we accumulate knowledge and we're like composing this knowledge when we learn, rather than we learn by contrasting continuously everything. And that again, it basically kind of forces you in a particular kind of solutions. And like at some point, people were there was this kind of big question of why people tend not to like replay methods for continual learning, right? They seem to be the most effective. Like what's the problem with replay? And I think replay methods are like a great tool, right? And there should be a lot more research on them, and I think they're probably part of the solution that we care about. But the reason, like, I think, if you have this perspective in mind, the reason why replay methods are not interesting is because they're avoiding the problem completely. So if you're taking this perspective in mind, then when you're trying to solve continual learning, what you're really trying to do is you're trying to find an alternative to gradient descent. You're trying to find a different way to assign blame to weights in such a way that you don't need to have this tension all the time, right? In a way that's a bit more compositional. And if you take this kind of perspective, you can think, well, continual learning is something super fundamental. It's something, in between optimization and learning, and it's about, it can change sort of how we think about the learning process itself. Okay, and I wanted to give an example on this, and yeah, so there's this really cool work from Tom Scholl. There's a lot more, there's a previous work from Andrew Sachs that was in the supervised setting. I like sort of the RL setting because it's very kind of intuitive. But there's this kind of really cool observation that Tom Scholl did in this work about ray hypothesis that shows how this kind of interference works in practice. And it shows that what really happens is if you have a neural networks, and this is an RL setting, but the same kind of holds in deep networks in supervised settings. You get sort of kind of this interference where trying to learn about mode A of your data distribution interferes with learning of mode B and forces you to learn this mode sequentially. And I find this very counterintuitive. So like one outcome of this work, and if you look at Andrew Sachs' work, it kind of says the same, is if you're trying to learn, you're doing multitask learning, so you have a series of tasks, and you're trying to learn them all at once, and basically that's the only way we know how to solve, to learn a model that knows how to solve n tasks at the same time is by doing multitask learning. If you check, what usually happens, or what happens more often than not, is that you learn the task sequentially. Everything breaks down if you give the task sequentially to the system. But if you give all the tasks at the same time, you're still learning them sequentially. You're basically kind of just burning cycles on the other tasks that are not really learning that much. I mean, you're not burning them for no reason. They have a purpose there, because otherwise learning would not work. But you're learning them sequentially, which I find quite kind of fascinating, because it seems like, well, yeah, sequential is what's going to happen. Like, learning things sequentially is what's happening anyway. It's just we don't somehow know how to make it work so that we don't waste that compute when we're kind of relooking at all of these tasks. And it also gives you like another kind of perspective, which says, well, if I have a huge data set like ImageNet that has lots of data, there's a lot of modes of the data distribution, and I learn those modes sequentially, even if I'm looking at all the data at the same time, then I end up wasting a lot of compute. And maybe this is the reason why deep learning is so data inefficient, and not data inefficient, but compute inefficient, why we have to do so many updates in order to kind of converge to anything, is because we're wasting a lot of compute because we have to learn this data mode sequentially. And then solving something like continual learning, maybe even in an ID setting, maybe even in a setting where, like we can control the stationarity of the data, might still give you a lot of data efficiency. And yeah, I guess sort of the I mean, these are, I'm not going to focus too much on this, but yeah, like I guess there are other ways of thinking about continual learning. And like, I guess one thing that I think is worth mentioning is kind of connecting continual learning to neuroscience, which is you can think of neuroscience as kind of something that guides you to know whether you're making progress or not in continual learning. And it's not the perfect thing, but like you can always look at like, okay, a biological system can do X, can my system do X? And that way you can, basically what that will help you is trying not to put too high bars, right? Like, we know we need to make some trade-offs, and you're trying to figure out what are meaningful trade-offs. And one way to do that is trying to understand what trade-offs a biological system do, and try to assume that CL can do the same thing. And I'm going to stop here so that we can have some questions. So this is kind of the summary. Quickly, I talked about learning on the fly, which I think it's sort of a way we should think about the systems. I talked about this idea that we can maybe think of limitations as a tool to shape our loss surface, rather than as something that we need to fight against. And I talked a little bit about continual learning and being somewhat undefined, and gave different ways you can conceptualize continual learning to kind of help you navigate all the different kind of variants of continual learning problems that are out there. Okay, and with that, maybe I'll jump to, there is already one question in the Q&A that asks whether CL can be used in low resource settings. So yeah, I mean, I think the typically in the literature, we're not focusing on low resources, but I think that is the goal. Like, particularly, I think in the last couple of years, there's been a lot of focus on forward transfer, and there's a bunch of papers out there, different people arguing that that's sort of one of the more important aspects of continual learning. And when people talk about forward transfer, one thing that they look at is area under the curve. So how quickly do you converge on the new task? And in some sense, that gives you a sense to, how helpful is this in low data regimes, or in like low resources kind of settings, because the continual learning system is supposed to, have a very quick convergence, right, to kind of quickly go down. So yeah, there's definitely. Are there any other questions?
Yes, one moment. So I
Okay,
can
so
read it
can you?
for you. Oh, yeah.
Okay.
Go ahead. Sorry.
Oh, okay.
Can you explain a bit more on non-stationary problem in continual learning?
Yeah. So again, like I think that people have tried to categorize this. So there's a lot of variants of non-stationary problems that people are using in continual learning. Maybe the most typical things, you have things like split CFAR, split ImageNet, where what you do is you take a typical IID data set, and then you split it along the classes, and then you first do 1 versus 2, then 3 versus 4, then 5 versus 6, and this is kind of the how you build on non-stationarity. But then people have been like building on this, and you have things like where you say you have a classification system that is trying to learn P of y given x, but the only thing that is changing is P of x. So was it clear? I think clear is the name of the data set. It's a pretty cool data set. They try to look at object as they evolve over time. So like think of seeing a phone from the 80s and then sort of images of the phone as it changed until today. And the idea is, you have a system that is doing n-way classification, say between a phone and whatever, and there's a distributional drift that it needs to deal with, which I think it's pretty cool. And like all other kind of variants, you have class incremental, all these kind of things, and there are like some really great surveys of continual learning, and if you look at them, you'd easily kind of navigate of what is the typical benchmark. I'd have to also emphasize that at the moment in the community, everyone agrees that the benchmarks that we have are not good for many reasons. There was actually some works that I had, some slides that I have after this, but I don't have time to go into them, kind of showing how some of these benchmarks might be way easier than we think, or might not really looking at the right thing. So there is that caveat, right? That there's lots of, there's a bit of a classification, there's lots of benchmarks, there's well-established protocols, but at the same time, no one is happy because, like you have this like the problem not being super well defined, and then depending on what you care, maybe the benchmark doesn't have exactly the kind of distributional drift that you might have in the real world, where you might want to apply that system, and then you get kind of stuck. Okay, thank
Next
you. Let's switch.
question. What would be the main difference between meta learning and continual learning?
Okay, so yeah, to me are quite different concepts. The idea in meta learning is that you want to, and again, sort of meta learning has multiple definitions as well, depending on sort of how you see the problem. But in general, in meta learning, you have access to a distribution of tasks that you can access in any way that you want. So there is no, like, non-stationarity doesn't come into play. The only thing you want to do is you're trying to extract some information about the learning process from that distribution of tasks that you can now exploit when you learn a new task from the same distribution. While in continual learning, I guess fundamentally the issue is the non-stationarity, right? So the way you see the data, you don't fully control the way you see the data, right? The idea is that the world is independent from you and it gives you data, and it's non-stationary, right? The data distribution changes that you see, and you don't have any control of that, and you're trying to make the best you can with what you have. So I think that's sort of one of the main differences. The other difference I would say also, like meta learning, it's kind of focusing on this kind of meta level, right? While in continual learning, we don't necessarily think that much of the meta level. So basically, putting it differently, we tend not to learn how to continually learn. We're trying to hard code how to continually learn, right? We're trying to come up with heuristics and theoretically well-motivated reasons of how you change your updates in order for the system to continually learn. But obviously there is a lot of common space in between them, and there's a lot of people that do. So you have, I think what I found funny is you have meta continual learning and continual meta learning, and they mean different things, right? So depending on which term goes first. So yeah, so there's a lot of in between.
Next question. Could you please talk about the evaluation in continual learning? You touched upon this a bit, especially the train test contamination problem.
Yeah, so thanks for the question. So I mean, I feel like I barely touched the surface, and I didn't really get to say everything that I wanted to say, which is always the case. I mean, I think these are really hard things to express. So like I think, like continual learning as it is right now is not really focusing on the test train contamination, but what is kind of trying to suggest, and I think where the literature is kind of getting to, is almost, if you're familiar, there's all this literature, Marcus Hutter is sort of pushing this quite a bit on frequential learning, and you kind of get in that direction where in order to try to figure out, how well the system is doing, you're looking to see how well it's going to learn on the new task. Frequential learning, it's a bit more, there's no concept of task, and the whole point there is that you have a system that is learning on a sequence of data, and you're always evaluating on a next data point in the sequence, and then you're integrating the area under the curve over this kind of evaluation, and the system that has the lowest area under the curve would be the system that generalizes the best. But the point here is that you don't necessarily need a train test separation anymore, right? You just have a sequence of data, and you're always just looking at what's going to happen on the next data point or on the next task, and that's sort of how you evaluate your system, and you're arguing that the optimal system is the one that is going to perform better on the next data point. And this kind of avoids to a certain extent, I mean, you still like maybe I'm being a bit I'm hiding things under the rug. You still have the question of, okay, like there's no stationarity. What defines this non-stationarity, which is kind of maybe close to the test train contamination. But I think it's a little bit less problematic than it is right now with this kind of large systems that we have. But it doesn't fully solve the problem, but it kind of pushes you towards this kind of sequential learning. And if you believe people like Marcus Hutter, he would argue that this is the answer to everything, and this sequential learning is the right way, that we should have always evaluated systems, and we should have never had a train test separation.
Can you speak a bit more about the trade-off between better future performance and catastrophic forgetting while engaging in continual learning? It seems like humans are able to learn new things and perform well in continual learning setting without succumbing to catastrophic forgetting.
Yeah, so I think it's a great question, and I think comparing it's always tricky comparing biological systems to learning systems, because I think there are different time scales at which things happen, and one needs to be careful. And it gets even tricky, like when you have parametric systems, like if we're thinking about transformers and language and stuff like that, we need to kind of slightly separate what's happening with the context versus what's happening with the weights. But yeah, I think catastrophic forgetting, it's in my mind, it's like a parametric, it's a specific phenomenon for parametric systems, and it has something to do with the update rules and the learning process that we have. And it's not clear to me that the brain or humans are relying on the same kind of learning rules or updates that our systems do. I mean, I would bet that most neuroscientists actually don't like the idea that we're doing gradient descent in the brain. I think that's just something that Jeff Hinton likes to say. Yeah, so the reason why this parametric system have this problem is exactly this kind of tug of war dynamics that gradient descent imposes, and there is no way around it, right? So the only way you can deal, if you're fully learning with gradient descent, the only way you can deal with this is you need to mimic this tug of war. So you need, if you don't want to look at some data anymore, because you've learned some mode of the data, you don't want to look at it anymore, in order to maintain the tension in a tug of war, you need to replace that data with something. And that's either like a regularization term, that it's trying to create exactly the same force that the data would have done, or it's the data itself, or by doing replay or things like that. And I guess the only way, another way that you probably could deal with this is if you could have local updates. If when I see a data point and I have a loss, I'm not updating all my parameters to answer to that loss. I know exactly, like, oh, okay, this I just need to change this particular weight, this particular module that is responsible for this kind of data. But we don't have that kind of machinery, or we don't have that kind of machinery that naturally emerges from the learning process. We maybe can impose it by hand, but then whenever we try to design these things by hand, we get them wrong, and we get this system that underperform. But yeah, I think that's the crux of the problem. Is like the gradient descent, the way it is, it doesn't work. It doesn't mean that we have to give up gradient descent. It might mean that we need to, I don't know, do something else. For example, like we need to modularize the system, and we need to limit gradient descent learning to particular modules, or I don't know. There could be all kinds of interesting solutions here, but I think fundamentally that's where the problem is. It's yeah, starting from.
Thank you. I guess no more questions. Thank you again for your talk. It was kind of diverse and was touching about important issue for the future of deep learning. I guess we can end this session.
Yeah, so if people have more questions or they want to chat more about any of these things, yeah, feel free to ping me, or Mohammed, maybe you'll let me know if there's anyone interested in having a chat, and definitely happy to do that.
Sure. Thank you.
Thank you.
Bye.
Okay. Bye-bye.